On behalf of the WM Keck Institute for Space Studies, or KISS, I'd like to welcome you to today's event. My name is Michelle Judd, and I'm the Executive Director of the Institute. KISS is a joint think tank between the Caltech campus and the Jet Propulsion Laboratory, or JPL. And we're focused on thinking up new ways of revolutionizing space exploration. We are privately funded, and so every dollar counts. So I'd like to thank the WM Keck Foundation for providing our first 8 years of seed funding. And I'd like to send out a very special thank you to our individual private donors and the Caltech Space Innovation Council, who are working hard to raise funds so our work can continue. So this lecture series is designed for the KISS affiliates, who are a small group of graduate students and postdocs who are nominated by the Caltech faculty to be able to interact with space exploration leaders and learn about new missions and ongoing missions like today's lecture. Sergio Parra is one of our 2020 KISS affiliates and is currently a third-year graduate student in the Geological and Planetary Sciences Division at Caltech. Sergio studies microbial activity in deep sea sediments, and he does that with various forms of microscopy. He focuses on this cool symbiosis between methane and sulfur-eating microbes. Speaking of eating scary things, as a microbiologist, Sergio enjoys fermenting his own habanero hot sauce. So let me turn over the program to Sergio Fear the Heat Parra. Sergio, take it away.
Thank you very much, Michelle. It is my honor to introduce our speaker today, Dr. Dante Lauretta. Dante earned his Bachelor's of Science in Physics and Mathematics at the University of Arizona in 1993. He went on to earn his PhD in Earth and Planetary Sciences from Washington University in St. Louis in 1997, and has been a professor of planetary science and cosmochemistry in the Lunar and Planetary Laboratory at his alma mater, the University of Arizona, since 2001. Dante is an expert in near-Earth asteroid formation and evolution, using both laboratory analyses and spacecraft observations to study the chemistry of asteroids and comets. Most relevant to today's webinar, he is also the principal investigator of NASA's OSIRIS-REx asteroid sample return mission and maintains an active research program in cosmochemistry and meteoritics. In addition to having an asteroid 5819 Loretta, named in his honor, Dante has written and co-written several books in his field and won various awards, including his selection as a Cobley Fellow of the National Academy of Sciences in 2008, and a 2010 recipient of the Antarctica Service Medal for his participation in the Antarctic Search for Meteorites program. Aside from his academic accomplishments, Dante is an avid game enthusiast and has designed 2 board games, including Extronaut, the game of solar system exploration, as well as Constellations, the game of stargazing and the night sky, the latter of which was a 2018 Mensa Select winner. I now realize that you've all come to hear him speak and not me, so without further ado, I'll now hand off the imaginary microphone to Dr. Lauretta himself.
Thank you, Sergio. It's great to be here. Very excited to present to the Keck Institute for Space Studies. I want to especially thank Kathleen and Michelle and the support crew who helped get this organized. They did a fantastic job, and I think this is the most organized webinar that I've participated in. So great work, and I'm glad to be here. So let's get started and talk about OSIRIS-REx, NASA's asteroid sample return mission. The mission is a partnership between the University of Arizona, my home institution, NASA's Goddard Space Flight Center, and Lockheed Martin. And our job is to get out to a near-Earth asteroid named Bennu, survey it in great detail, and bring a sample back to Earth for analysis in our laboratories. So just to make sure we're all on the same page here, I've got a very simple schematic of the solar system. Note that the sizes and the distances are not to scale. It's just to orient ourselves quickly to the overall structure of the solar system. Of course, at the center, we have our host star, the sun. In the inner solar system, we have the so-called terrestrial planets, compositionally dominated by rocky silicate material and metallic material, with small concentrations of critical elements that we call volatiles, like hydrogen and oxygen in the form of water, carbon, nitrogen, and other key prebiotic elements that go into forming biomolecules here on Earth. Those are actually quite rare in the terrestrial planets, but important for habitability of planet Earth, for the origin of life, and everything that got us to this point today. In the outer solar system, you have the gas giant and ice giant planets, and separating those, you have a belt of asteroids, which is a geologic remnant from the dawn of our solar system. Basically, the massive gravitational field of Jupiter continuously perturbs this area of the solar system, preventing this material from accreting into a larger planet. So it tells the story of how our solar system came to be and how the terrestrial planets formed, and hopefully how Earth in particular became a habitable world, maybe also Venus and Mars. So when we're designing an asteroid sample return mission, our first thought was we should head out to the asteroid belt, get something right from the source and bring it back home. We quickly realized that that's a very expensive prospect, expensive in terms of energy, time, and money. And when you're designing a NASA or any planetary robotic exploration mission, you're always balancing those resources. Fortunately, we didn't have to get all the way out to the asteroid belt. Jupiter continues its role in perturbing the bodies, the small bodies of that area of the solar system, causing them to collide with each other, sometimes catastrophically, creating thousands and thousands of fragments. Some of those fragments are perturbed through gravitational interactions with larger asteroids, also with the giant planets. And then it turns out that sunlight plays an important role in influencing the orbits of small bodies, particularly those below a kilometer in diameter or so. And that's called the Yarkovsky effect. And those forces combined push a small percentage of the asteroids out of the main asteroid belt into inner solar system crossing orbits. And when they do get reasonably close to the Earth, we name those near-Earth asteroids. I kind of like to think of this as the asteroid belt as the mountain, and the near-Earth asteroid is the stream bed. If you want to figure out what the mountain is made out of, you could climb all the way to the top, get your samples and bring it back. Or you could poke around in the valley right below the mountains in the stream bed and see all the different kinds of rocks that are tumbling down. That's basically what we're doing. We didn't have the energy or the time to get out to the main belt, but we know fragments of those asteroids are tumbling into the inner solar system. So we targeted a near-Earth asteroid for our mission. Now, I've been on this program for what seems like a long time, since 2004. Sergio mentioned I came onto the faculty here at U of A in 2001. So within 3 years, when I was still a young assistant professor, I got a phone call from the director of the lab, Dr. Michael Drake, inviting me to join him on a NASA proposal to go get an asteroid sample and bring it back to the Earth. It was kind of a hard decision in the sense that when you're at that stage in your career, you're juggling a lot of responsibilities, always focused on your tenure package, and you want to make sure you're using your time wisely. But the opportunity was so amazing, I couldn't say no. And I said, okay, Mike, what do you want me to do? And he said, as the deputy principal investigator, your job is to define the science program and tell the agency why we want to get those samples back. So I took that to heart. I wrote down 4 words: origins, spectroscopy, resources, and security, defining the 4 key areas of investigation for a near-Earth asteroid. I already mentioned our origins. When we go to asteroids, we're going to the oldest geologic material in the solar system, and it tells the story of planetary formation and solar system evolution. There's over 1 million asteroids in the solar system, and probably more are being discovered every day. We're never going to send a spacecraft out to every one of those. We study most of them telescopically, and we learn a lot using spectroscopy, which basically breaking light up into its constituent wavelengths, looking at the different intensities. Where you see the intensity dropping, it's an indication that there's a specific chemical bond on the surface that's interacting with that reflected sunlight. And so you can interpret the composition of the surface. The challenge with the kind of asteroid that we're targeting in this mission is that they're very dark and the spectra are very subtle. So we want to have this ground truth sample in our laboratories so we can better understand this compositional variation of asteroids throughout the solar system. When I wrote down resources in 2004, I thought I was just letting my sci-fi geek flag fly. But it turns out over the past 2 decades, people have gotten more and more interested in asteroid mining and resource extraction. And I've seen companies rise up in the United States to pursue this and then go bankrupt. And now a new wave of companies is coming forward. So the idea has some interest. And I would love to see OSIRIS-REx be a pathfinder for true economic development of asteroid resources. And security, we're talking about near-Earth asteroids. They're relatively easy to get to in terms of energy, delta V, the currency of the solar system, the change in velocity required to rendezvous with a specific target. But that means they're also easy to come to us. And we know throughout geologic history, asteroid impacts have caused large-scale environmental disasters leading to mass extinctions of life on Earth. We're the first species capable of deflecting an asteroid potentially. And so it's a key part of our investigation is to understand asteroid impact hazards and develop techniques potentially to mitigate those in the future. And then when we get out to the asteroids, they're airless bodies. The material that covers their surface, this blanket of loose rock and gravel we call regolith, and that's what we're after. We're exploring the regolith on the surface of the asteroid telescopically, spacecraft-based, and also ultimately in our laboratories. So we selected a particular near-Earth asteroid as the target of our mission. It's asteroid 101955 Bennu. And we knew a lot about this object prior to launch. It is by far the most well-characterized solar system object telescopically. Every glass that we could get on Earth, we had access to. We used the Hubble Space Telescope and the Spitzer Space Telescope, the Herschel Space Telescope. We understood its orbit very well. Over here on the upper left, you can see the orbit of the asteroid in blue. The sun is at the center. The orbit of the Earth is in green, and you can see right here, this horizontal line where it intersects the Earth's orbit is the vernal equinox. And when you take a look obliquely, you can even see Bennu's orbit, in fact, comes right past the Earth. It's a bit eccentric. It gets out almost to the orbit of Mars and comes in at perihelion closer than the orbit of the Earth does. So its period is 1.2 years. So every 6 years, Earth has gone around the sun 6 times. Bennu has gone around the sun 5 times. And so every 6 years, they do a close approach to each other. And that sets the observing cadence and also our mission timeline. Some of the most remarkable data that we collected is shown over here in the upper right. This panel that I'm highlighting with my cursor is raw radar return data from the Arecibo Planetary Radio Telescope in Puerto Rico. And we actually just got some bad news this month that there was some extensive damage to the telescope. And the National Science Foundation has decided to decommission Arecibo, which is a great loss, not just for asteroid science, but for radio astronomy broadly defined. We were able to take that Arecibo data. Bennu came really close to the Earth within a couple of lunar distances during its discovery apparition in 1999. And we were able to get about 7.5 meter resolution of the surface. These images are a little difficult to interpret. They kind of look like an image, but they're not really an image. And through a forward modeling process, we take all of the radar data and we're able to reconstruct a 3-dimensional shape model that is then found to be consistent with the data within some convergence criteria. So we knew a lot about the asteroid from this data set and from the other astronomical characterizations. We knew its size. It's about 500 meters in mean diameter. It has a fascinating shape. It's almost a sphere, which is unusual for such a small body. A spherical shape is usually obtained by a planet when it reaches hydrostatic equilibrium with gravity and fluid interior. The fact that Bennu and other near-Earth asteroids share this morphology is also close to a sphere, indicates that it's fluid-like in some way in its behavior. And it has this spinning top characteristic where the equator bulges and has a larger radius and it's kind of flattened at the poles. It spins every 4.3 hours. It's a retrograde rotator, which means its obliquity is 180 degrees, or its north pole points south in the solar system coordinate system. We did some amazing work combining radio astronomy with infrared observations. We measured the Yarkovsky effect, which I had mentioned earlier. It's when sunlight interacts with the surface of an asteroid, heats it up. That energy is re-emitted back into space as thermal radiation, and that emission, anisotropic emission, imparts a thrust on the asteroid in the direction of its afternoon. Since Bennu is a retrograde rotator, its afternoon is in the direction of its orbital motion. The emission of that radiation slows it down, reducing its orbital velocity, and that's a function of its mass. So we're able to measure the mass from our Yarkovsky detection, and then we had the volume from this amazing shape model that we produced, and we got a bulk density of 1,260 kilograms per cubic meter. Very low. Your average rock is on the order of 3,000 kilograms per cubic meter. Carbonaceous chondrite meteorites, which we think Bennu is related to, have lower densities around 2,000 kilograms per cubic meter. This low density suggests that Bennu is not a solid mass of material, but it has a lot of porosity, a lot of void spaces in its interior. And its albedo is very low. 4.5 albedo means 4.5% of the sunlight that hits its surface is reflected, and 95.5% is absorbed by the surface. So it's quite dark, and we think that's due to the presence of carbon on its surface. And the key objectives of OSIRIS-REx were to find an object that carried the kinds of volatiles, the water, the organic material that made Earth a habitable planet and ultimately may have led to the origin of life here. So we specifically chose Bennu because of its very favorable orbit, nice large size to enable spacecraft proximity operations, and composition, which suggests that it contained information about the formation and evolution of organic material and represented the kinds of bodies that may have brought the seeds of life to Earth. We also use the radar data and the infrared data to characterize the surface and get a sense of what we might be up against with this mission. We saw only one boulder on the surface, highlighted with these little white arrows on the upper left diagram here, on the order of 10 meters. Otherwise, the surface looked really smooth. We measured a property called thermal inertia, which measures how fast an object heats up and cools off. That number was very low. It's 310 in these SI units here. Basically, it's a combination of heat capacity and thermal conductivity. Bedrock was thought to be around 2,500. So as this value drops, you usually go from large boulder-sized objects down to fine grains. So we took this information and we estimated that the average grain size on Bennu was on the order of 1 centimeter, and that it was generally going to be a smooth surface with very few boulders. In fact, I used the term beach-like as we were going through development and we were designing the spacecraft and the sample collection mechanism. We thought we were going to get into a fine-grained asteroid surface, and our TAGSAM collection mechanism was designed around that. This is a high-level view of the mission timeline, and I'm going to talk through some of the key discoveries that occurred throughout this, culminating with our amazing sample collection event last month. Spacecraft launched in 2016. It's a little over 2 years to get to Bennu. We've been operating around the asteroid since late 2018. We collected the sample in October, and now we're preparing for a departure maneuver. The earliest we can leave the asteroid is March of 2021, and we have a departure window, very much like a launch window, that extends into May of 2021. And we're currently going through a trade to decide what is the best time to leave to optimize the Earth entry interface for sample return, which will occur in late September 2023. So what we did with this program was build what I call the ultimate asteroid robotic exploration vehicle. And one of my favorite parts of being the principal investigator of the program was to be there during what we call the ATLO phase of the mission, assembly, test, and ultimately launch operations. I got to go to the clean room at Lockheed Martin's facility in Littleton, Colorado, talk to the technicians who were assembling the spacecraft. They were very excited about the mission, told them all about the science that we were going to achieve, and literally watched this machine get put together in front of my eyes. And very capable science investigation and really a sample collection spacecraft. This is an overview of the instruments on our payload deck. We have a whole series of cameras. We've got the Polycam, MapCam, and SamCam that comprise the OSIRIS-REx camera suite, or OCAMs. Polycam is a telescopic imager, also includes a focus mechanism. So when we're close to Bennu, it becomes a microscope, which is why it's the Polycam. The MapCam is our mapper. It's got color filters, so we can look at the color features on the surface. And the SAMCAM was there to document contact with the asteroid surface to see what happened when we were collecting our sample. We have several spectrometers. OVIRS operates in the visible and infrared, and OTIS in the thermal emission region, or the mid-infrared. Both of those are point spectrometers. OVIRS covering the wavelength ranges from 0.4 to 4.3 microns, and OTIS picking up at 5 microns and going out to 50. We had a student X-ray imaging spectrometer called REXIS, which was looking for X-ray fluorescence from the surface. Our sample collector is the TAGSAM, the touch and go sample acquisition mechanism. You'll see a lot more of this, but it's on a long robotic arm. Here it is packaged up in a safe container for launch. We have our sample return capsule, which is how we'll get the sample back down to the surface of the Earth, and provided by the Canadian Space Agency, the OSIRIS-REx Scanning Laser Altimeter, or OLA. We also have a couple navigation cameras, which you can see just tucked over here, our NavCam 1 and 2, and then a little camera over here called the STOCAM, which is looking right at the sample return capsule, and we'll see images from those devices as well. This mission is all about sample return. It is our primary objective, and it's the driving requirements for the program. The level 1, which is the top level requirement, basically my agreement with NASA on what this mission will deliver. We were there to collect at least 60 grams, or about 2 ounces, of pristine sample from the surface of the asteroid. And that pristine was important because we're interested in the organic chemistry of Bennu, and we want to know if objects like Bennu delivered the seeds of life to Earth. We're talking about fundamental molecules like amino acids, which build up our proteins, and nucleic acids, which combine together to make DNA and RNA. We want to make sure we're not contaminating the sample with those compounds from Earth, so we can truly tell if they're coming from the asteroid or not. We also have a second collection mechanism, which relies on a series of contact pads. So just by touching the asteroid surface, we would collect material from the asteroid. So the bulk collector this is a very early prototype of the TAGSAM device. And I particularly like this photo because it really shows you the kind of surface that we were originally envisioning sampling, this nice sandy kind of material. And then you can see this is after a collection test, how the TAGSAM works. So this device at the end of the robotic arm is basically an air filter. And we push this down onto the asteroid surface, and you can see where it makes contact. There's a whole ring defined in the sand here. And we have 24 individual contact pads, which are made out of the loop side of stainless steel Velcro. And that actually acts like little tweezers, and it grabs particles up to 1 millimeter just by touching the asteroid. And then TAGSAM has a series of gas bottles of high purity nitrogen further up on the robotic arm. And when surface contact is sensed, it opens one of those bottles and it blows down material and pushes the regolith up into the filter where it is captured for return to the Earth. Here's a better view of TAGSAM as it was deployed on the ATLO floor. So we had a gravity offload fixture here. And then here's that sample head kept clean and pristine throughout the entire assembly. Here you can see 2 of the nitrogen bottles. There's a third bottle that's out of the view here. And then this is the lower portion of the arm. There's 3 motors, a wrist motor, an elbow, and a shoulder. Total length of the robotic arm is about 3 meters, or just over 9 feet. And then this is the strategy. The entire spacecraft is designed to descend down to the asteroid surface. TAGSAM makes contact. The spacecraft senses that contact either through accelerometers or through a micro switch. The forearm actually compresses like a pogo, opens up one of those gas bottles. We blow down the gas for about 5 seconds, and then we fire our back-away thrusters and leave the surface of the asteroid. Once we're confident that we've collected enough sample, we open up the return capsule, kind of like a clamshell. We place the filter into a capture ring. We detach both the gas tubing and the bolts that hold the TAGSAM head to the arm, and we close it up for journey home. So in 2011, the program was selected for implementation. And that was in May of that year. And I mentioned I was brought on as the deputy principal investigator. And tragically, in September of that same year, 2011, Mike Drake, my friend, my mentor, and the original PI for this program passed away. And the mantle was given to me to continue to lead this program forward. We spent the next 5 years going through design, build, test, and ultimately launch operations, getting to the point that you see here, where we're doing final processing at Kennedy Space Center in the Payload Hazardous Servicing Facility, an amazing historic location where dozens of interplanetary spacecraft have passed through on their journey into the solar system. And then over here, you can see our itinerary launching in September of 2016, noting that that's when Bennu's ascending node crosses the orbit of the Earth. So that's why all the fun stuff happens in September. We came back a year later for a gravity assist. We started observing Bennu in August of 2018 and arrived in December. Sorry. We've been performing asteroid operations ever since, leading to sample collection in October of 2020. We're planning a departure maneuver. April's right in the middle of our window, but we haven't selected the date yet. And then it's a over 2-year cruise back home, with sample return again occurring in September, this time in 2023, kicking off the final science campaign, which is analyzing the samples in our laboratories. So launch was absolutely flawless. It was a beautiful day in Florida, sending us on our journey to asteroid Bennu, and we arrived in December of 2018. Every year, the mission produces a commemorative poster, and there's also a pin, a lapel pin, and stickers and patches that go with it as well. This is one of my favorites, the Bennu arrival poster. And then traditionally every February, the mission releases little Valentine's Day cards, and you can find those on our website, asteroidmission.org, and I'll have them sprinkled throughout the presentation too. So the original job on our way in was to search for any hazards that might be present in the asteroid operational environment. We know that a lot of asteroids are binaries. They have satellites. We didn't see any evidence of a satellite around Bennu from the ground-based characterization, but nevertheless, we were worried about anything on the order of 10 centimeters in diameter or larger that might pose a hazard to the spacecraft were we to collide with one of those. Everything looked great. We used the Polycam. We searched down, as you can see, this within, remembering Bennu is 500 meters across. This inner circle is a 300-meter radius, so it's just outside the edge of the asteroid. We're able to view in here, and we didn't see any sign of any satellite or particles or dust in the environment. It looked nice and clean, and we proceeded in to the asteroid. And it started to look pretty good. The early images suggested that our astronomical campaign was spot on. You can see the shape model over there on the right from the Arecibo data, and then the first look images on our way in on the left. And we really nailed it. We got the shape, we got the size, we got the rotation state, all really close to reality. The one boulder that we saw from Earth, you can see just come into the field of view here, was definitely there. A little bit larger than we expected. But in these images, we started to get a hint that maybe the surface wasn't quite as smooth and beach-like as we had inferred from the astronomical data set. And then right at the arrival point, early December of 2018, we got, which to this day are still some of my favorite images from the program. We had the full disk of Bennu in our Polycam field of view, 33 centimeter per pixel resolution, and we're able to snap these dozen images to show the entire rotation of the surface of the asteroid. Then these images came down, I started to get a little worried. I was like, that doesn't look like the average grain size is on the order of a centimeter on the surface of this asteroid. I'm seeing some pretty large boulders. We have the big one down here, which we now call Ben Ben, but there's plenty of other ones that are that size or larger that weren't showing up in the radar data for some reason. I also didn't see anything that looked beach-like. There was no really clear patch of fine-grained regolith. And we had thought that with this bulge at the equator, that this was due to migration of samples or of regolith from the polar regions accumulating at the equator And we thought that this bulge would be built up of gravel-sized particles because those were expected to be the most mobile. There's no indication of that there's any kind of grain size sorting going on anywhere on the asteroid surface. So right away, early in the campaign, we knew we had a challenge to find a site that was safe for sampling. And then we got into orbit on New Year's Eve of 2018. Less than a week later, January 5th of 2019, we started to see images like the one that I'm showing you here. So this is from the navigation camera. These cameras were being used for optical navigation around the asteroid, and they were taking two exposures. They were taking a short exposure to resolve features on the asteroid surface and a long exposure to see background stars. And using those two methods combined, they were able to really accurately determine the location and velocity of the spacecraft. So this image is a composite. The Bennu surface is from the short exposure, and then this area here is from the long exposure. It looks like a star cluster, except there's no known cluster in this part of the sky here. And it turned out that this was Bennu ejecting particles into the asteroid environment. And because we were doing optical navigation, we had a series of images. We could actually see the relative motion of the particles. And our navigation team, being experts in orbit determination, were able to take that data and determine the trajectory of hundreds of particles from discrete ejection events. So you can see here, this is reconstructed trajectory information from a whole series of particles identified in a single ejection event. Because Bennu is so small and its density is so low, the escape velocity is on the order of 10 centimeters per second. So anything that's coming off the surface faster than that is gone. And you can see a whole series of trajectories going off to the right of the image here. And those are now lost from Bennu, and they're part of the interplanetary dust population. But a large fraction of the particles are coming off at much slower velocities and are basically on suborbital trajectories. And it turns out some of the particles that get lofted way up get accelerated by solar radiation pressure and go into extended orbits around the asteroid. So at first we were concerned that this was going to be a safety hazard to the spacecraft. And we did a bunch of analysis to determine the sizes of the particles and their velocities. And we saw most of the particles are on the order of a centimeter or so, less than half an inch. The biggest one is about 10 centimeters, so that's pretty big. But they're moving so slow. They're moving at 10 centimeters per second, similar to the spacecraft orbital velocities. So they would just hit the spacecraft and bounce off. So we very quickly ruled out any hazards to the spacecraft from these phenomena. And then it turned out to be a fantastic science campaign, because by tracing these trajectories and by modeling solar radiation pressure and other small forces, we're able to use these as mini gravity field probes. We're able to measure the gravitational field to a much higher precision than we expected to be able to just from tracking the spacecraft alone. So we got a fantastic gravity field solution to 8th degree in order. If you're familiar with the spherical harmonic expansion for gravity field, the mission requirement was 4th degree in order. So we absolutely nailed it and did amazing gravity field science, along with a lot of other cool science from understanding the particle ejection events. What's causing this? Well, we've really nailed it down to about 2 or 3 possible mechanisms. All of them seem likely, and they may all be in play here. So the first one is micrometeoroid impact. Bennu's getting hit by a 100 millijoule micrometeoroid every minute. And that 100 millijoule energy value was chosen because that was the total linear kinetic energy that was observed in the largest particle ejection events. And quite honestly, when I did the calculation and I saw that number and I was like, 100 millijoules, that's nothing. That's hardly energy at all. So that confirmed the safety assessment that there's no risk to the spacecraft. We're seeing these ejection events about every 2 weeks or so. They're very common. We've seen them going on through the entire asteroid encounter. When we apply the micrometeoroid flux model to that time frame, we see that about every 2 weeks, a 5 kilojoule impact occurs. So these are very likely candidates to be ejecting particles. The other thing we looked at was, Bennu's spinning around once every 4.3 hours. It's getting hot, it's getting cold, about 200 degree temperature cycle every 4.3 hours. So it's getting thermally stressed, right? When you heat up a material, it expands. When you cool it off, it contracts. You're doing that every 4.3 hours. You're building up stress fields in the minerals inside the rocks. And eventually they can fracture. And we see this happening on Earth in some of the granite domes in Northern California. When they heat up, they're releasing energy, usually stored up energy from tectonic forces from being compressed deep within the Earth's crust. Jumping ahead a little bit, but we do know that Bennu, it contains abundant hydrated minerals in the form of clay or phyllosilicates, and that this stressing may be causing dehydration reactions and taking the water out of the crystal structure and putting it just as absorbed molecules. And so these thermal forces may be also driving these particle ejection events. And then finally, we see that these particles are falling back onto the surface of the asteroid. So it's possible that a secondary impact, kind of a momentum transfer, could have a knock-on effect. One particle lands and it either bounces and goes back into orbit, or it imparts its energy to another particle, which then is launched from the surface. And we actually do see one particle bouncing off the surface of the asteroid. It's in that Chesley et al. 2020 publication that I've cited there. Fascinating to see this totally unexpected and dynamic environment. And there's a lot more I could tell you about this. We had a science paper that announced the discovery, and then a whole special issue of JGR Planets dedicated to exploring this phenomena. We did find out that Bennu, in fact, that we got the mass and the density correct. We were able to measure the density initially with hyperbolic flybys of the spacecraft over the asteroid surface, and then once we were in orbit, and then we nailed the shape model as well, and we got a density of 1,190 kilograms per cubic meter, about the same as that 1260 that we measured from the ground. So we confirmed that pioneering technique for determining asteroid masses, which means we can apply that with confidence to all kinds of near-Earth asteroids. And obviously, mass is a critical parameter when you're assessing an asteroid as an impact hazard. So Bennu definitely appears to have a very high macroporosity. We think it compositionally looks like some known meteorites called carbonaceous chondrites. And those, as I mentioned, those have densities around 2,000 kilograms per cubic meter. So that means that Bennu volume is about 50% void space, or 50% macroporosity. So we really think it's a pile of rubble, that it's not a coherent body, that it is behaving somewhat fluid-like, and that the particles are very loosely connected to each other. And then the question is, well, how did we get the grain size so wrong from the ground-based observations? And the key value that we looked at was that thermal inertia. And I mentioned this before, but thermal inertia is how a material responds to heating. If you have a low thermal inertia, that means you have a low resistance to changing your temperature. You heat up and you cool off very quickly. If you have a high thermal inertia, you heat up and you cool off much more slowly. And we got that number right. We thought it was 310. We confirmed that, it's about 350. That number, very similar to what we got from the ground-based observations. But what didn't occur was that this low thermal inertia does not correspond to small grain sizes. So what's going on here? When we look at the surface of the asteroid, and note this is one of my favorite images of the surface, got a couple of my favorite features in it. Field of view is just under 70 meters across. So you can get a sense this boulder outcrop here is on the order of about 15 meters tall. And it's one of the darkest objects on the asteroid, and it's also where the low thermal inertia material is. So it looks like these boulders, we call these the dark hummocky boulders, and there's a lot of them on the surface of the asteroid. They appear themselves to have very low thermal inertia. So they're either covered in dust, they're a mixture of regolith and boulders. They're very loosely collected together, so they're very materially weak. And so we think that it's simulating kind of beach-like material. We call this one here, just as a little fun fact, this is gargoyle saxum. That's been approved by the International Astronomical Union. I think, he's got a jewel on his wing over here, and this is his beak. And then right next to it is Osprey Crater, which is one of our final 4 candidate sample sites. Let's switch over now to just a brief discussion of the chemistry of the asteroid. It's always hard to talk about spectroscopy in these kind of public forums. So I'll do my best here. This is a graph showing you the wavelength of the light that we're looking at from OVIRS. That's our visible and infrared spectrometer. We're well into the near infrared in this wavelength range here. Humans can't see much past 0.8 microns or so. And we're looking at a very specific region here because here's some famous carbonaceous chondrite meteorites of the kind that we're hoping Bennu might be related to. And they have a very distinctive spectral absorption. So if there was no chemistry influencing the reflectivity, this would be a flat line all the way across. But then you see here, instead of that happening, the wavelength is relatively flat, and then it hits this region around 2.7 micron, and the signal drops substantially. That's telling you that there's some chemical compound on the surface that has a bond whose excitation energy is comparable to the photon energy here. And we know that is the hydrogen-oxygen bond of water. So you can see all of these chondrites have that characteristic absorption from the hydroxyl molecule, and Bennu shows that as well. And we saw this very early in approach phase of the mission, and it's been consistent throughout the entire characterization of the asteroid. Bennu is loaded in hydrated clay-bearing minerals. It's got a lot of water on its surface. Anywhere from 5 to 10 weight% of the asteroid is probably water alone. And that's exciting for all kinds of regions, for our origins investigation, but also for that resource characterization, because the primary commodity that asteroid miners are targeting is water, not because you can drink it, but because you can break it up into hydrogen and oxygen, which is a very powerful propellant. And the strategy is that would be used as like gas stations on Earth. And then just recently, we published the discovery of carbon-bearing molecules on the surface. A lot of organics are discovered there. I got particularly excited about the region. Now we're still looking at OVIRS here, but we're looking at the wavelengths of 3.4 microns or so. And this is where carbon-hydrogen bonds and carbon-oxygen bonds are active. And most of the spectra look like organic material, but some of them look like minerals, carbon-bearing minerals like carbonates, particularly calcite. And we saw that these were correlated with specific kinds of boulders, and one of them is over here on the left. And what struck me right away was this very bright material. We did calculate the albedo, remembering Bennu's albedo is about 4.5%. This rock's a little brighter than that. But these veins are 15 to 20% reflectance, very, very white, bright materials, just like carbonate minerals. So, and these are getting quite long. Some of them are approaching 1 meter in length. They're tens of centimeters thick, which means that Bennu couldn't have had a hydrothermal system capable of forming these kinds of minerals itself. It must be a small fragment or series of fragments from a much larger asteroid, probably on the order of 100 kilometers in diameter. And that object had to have a massive hydrothermal system with fluid flow extending for thousands to millions of years to precipitate the kinds of minerals that we're seeing here. So we're getting a nice look at the history of Bennu. As part of that publication series, we also published the color maps of the surface. Bennu is generally a blue asteroid. So here we've combined 3 of the color filters of MapCam and this false color imagery. But in general, Bennu does get more reflective at the shorter wavelength. So it really is a blue asteroid. But you can see right away, it's got a lot of color variation on its surface. And the things that jump out at you are some of these red, what look like little pockmarks. When we zoom in on those areas, we see that those are actually small impact craters. And they're very distinct. They're bright red compared to the general blue, or I should say redder than the general blue background of the asteroid. And then we look at the size frequency distribution. There's dozens of these identifiable. You can see several of them just in this single field of view here. And we can see that it's a very young crater population. And it's consistent with the impact flux in the inner solar system. And in fact, we think these red craters are only formed within the past 100,000 years or so. That's going to be really important when we get to sample site discussions, because where we got the sample was from inside one of these red craters. So I only hit some of the real highlights there. We did an enormous amount of amazing asteroid science during our asteroid encounter in 2019 and publishing it throughout 2020. noting that we were on the cover of Science back in November. So with all of that information in mind, we had the right asteroid. It's got water, it's got organic material, but we had to find a spot on the surface where we could go and collect the sample. And that was a combination of engineering constraints. Could we get in there? We're going to get into a really tight spot. Is it safe? Is there anything for TAGSAM to grab? TAGSAM was designed to pick up 2-centimeter particles and smaller, and it wasn't clear that there were areas like that on the asteroid's surface. The only thing that was easy was the science value. Bennu is exactly like what we wanted it to be compositionally, and we're really excited to get those materials back to the Earth. And so I won't go into all the details here, but we had an extensive campaign to select the sample site. It was quite a lot of fun and a challenge, and we ended up with what we call our final four different regions on the asteroid surface. And I'm just showing you real data. This is a combination of the topographic information from OLA and the imaging data from the Polycam. We name all the features on Bennu after birds or bird-like creatures, and the sample sites were all named after birds that are native to Egypt. So we had the Nightingale crater in the upper left, the Osprey in the upper right, a small crater called Kingfisher in the lower right, and then a wall of a much larger crater shown in the lower left there, the Sandpiper site. We ultimately selected Nightingale as the primary sample site. It wasn't the safest. It actually has some hazards that we need to worry about. I call this big boulder over here on the right, Mount Doom. This one we're really worried about the spacecraft maybe colliding with either on the way in or more likely on the way out if there was any kind of tip over. But once we got into this scale, this crater is about 20 meters in diameter, about the size of a tennis court. You could fit right inside this crater easily. You can tell it's very different than the background terrain of the asteroid. It is relatively smooth. It was the closest thing to a beach-looking surface that we had. We were able to characterize this site in incredible detail. And so this is this is the best imaging mosaic that we got of the Nightingale site using Polycam now in that microscopic imaging mode. Notice the ragged edge here. These are individual images that we have mosaic together by our amazing image processing team here. So this is 100 images or so that's stitched together to give us this nice high resolution mosaic of the Nightingale site. And then I'm going to zoom in on this little box here. The width of that box is only 3.5 meters. And so you can really start to see individual grains, and you get a sense that actually there are centimeter scale and even smaller particles that are visible when we map at this resolution. So after we got this information, we knew we were in good shape. This was the right site as long as we could keep the spacecraft safe. In order to verify that and to really target the best location, I had a team here at the University of Arizona that were expert asteroid rock counters. And they did an amazing job. You can see the data set that we collected just in the center of the Nightingale site. Notice the blue circle is is what we call our 80% confidence area. This is 80% likelihood the spacecraft would contact within this area here. And note the scale bar, it's only about 8 meters across or so. Anything that's yellow is the kind of particle that TAGSAM can collect. So yellow is what we want. And then the color scale goes all the way up to red. 21 centimeters was thought to be a deal breaker. If we landed on something that big, it could have blocked the entire sample collector completely. So over here on the left, I show you all the rocks that we counted. And then over on the right, only the yellow ones. That is the ones that we identified less than 2 centimeters. And you can see we targeted a center of the site that had a high density of collectible material. So that we were highly confident going into sample collection that we had the right site. I don't go into all the operational details here, but the team did an amazing job improving the guidance system so that we could fit into that very tight spot. And then on October 20th, just last month, we went in for sample collection. And there's a series of maneuvers. So this just shows you the asteroid and then the OSIRIS-REx trajectory as we're coming in. So we're in orbit prior to this. We actually departed orbit, targeting an area over the asteroid surface we call our checkpoint. We fired the rocket engines, changing the trajectory of the asteroid, of the spacecraft, sending it down to the surface of the asteroid. And then about 50 meters above the surface, we fired the thrusters again at a maneuver we called the match point, and that matched the rotational velocity of Bennu so that we were descending down to a single contact point. We have figured out exactly where we touched down on the asteroid's surface. We had 3 different teams reconstructing this. The blue dot on the little map over there on the right is from our onboard guidance system, our natural feature tracking system. And that's overlaid on what we call the hazard map. So anything that was green on this image overlaid on the Nightingale crater was safe. Anything that was red was hazardous, and that Mount Doom boulder that I talked about, which is about the size of a 2-story building, was clearly not an area we want to contact, so we painted that red. And then we added some margin, so anything that was yellow was also just deemed unsafe for us to contact. The navigation team did an orbit determination, or an OD reconstruction, and calculated that we hit at the magenta dot. And then the image processing working group, or the IPWG, which I think is the most accurate one because they're actually registering us to the images themselves, had the orange dot. All of them are in a pretty good agreement. I mean, they only differ from each other by 20 centimeters, 25 centimeters or so, which is smaller than the diameter of the TAGSAM head, which is 30 centimeters. And then the black dot is where we were targeting. So we landed within a meter of our predicted location. And it was a great spot. This is a really cool stereo pair. One of our science team members is Dr. Brian May. You may also know him as the lead guitarist for Queen. And he's an expert in stereo imaging. So he was able to take 2 images, one from the MapCam, which was taken about 4.5 minutes before contact, and one from the SamCam, which was about 30 seconds before contact. And this is a stereo pair. So if you're good at these kinds of things, you can cross your eyes and you can see the 3D structure of where we contacted. The red circle is the diameter of TAGSAM. So we're still a little bit above the surface here, and we're coming down to make contact, but it looks pretty good. This one boulder that I'm highlighting was a little bit concerning. It's right at that 21 centimeter mark. And I thought when I first saw these images, maybe half of the sample collection area might've been blocked. But otherwise, actually, everything went really well. So the image sequence that I'm showing on the right is right before contact and right after contact. And that boulder that I told you I was worried about is right at the top, the 12 o'clock position of TAGSAM. And it just crumbled underneath us. It literally just shattered into small dust fragments, and we penetrated into the surface. And I can say, we tagged, in the afternoon on October 20th, and I stayed up till 2 in the morning because that's when these images were downlinking. And as soon as I saw that second image, when TAGSAM hit the surface and pushed in, I knew we had the sample. So we got in about 4.5 centimeters prior to firing our gas bottle. We compare this kind of condition to our laboratory tests. Those tests were picking up over 1,200 grams of material. Remember, our requirement is 60 grams, so this was very promising. We also got our rock counters going, and I said, okay, tell me how many rocks are there underneath the TAGSAM head where we contacted that are less than 2 centimeters. They counted 35 individual stones that are probably inside the TAGSAM head right now. When we take that particle size frequency distribution and we run it through what we call our sampleability algorithm, which takes all of our laboratory testing and quantifies the collected mass, we're predicting that we would have picked up between 258 and 575 grams of sample just from the surface. This doesn't consider the fact that we actually continued to penetrate for 6 more seconds, and we got as deep as 48 centimeters into the asteroid surface. Really buried the TAGSAM arm quite far down. So there's probably more than what the sampleability algorithm would predict. And then finally, we saw the asteroid surface response was just phenomenal. We were digging down into the surface throughout the entire collection event, and we were able to reconstruct what happened. So the contact was sensed by our accelerometer. The surface was very weak and compliant. On the order of 10 newtons of force were pushed back on us from the surface. As planned, 1 second after contact, the TAGSAM gas bottle fired. We let that go for 5 more seconds. So 6 seconds after contact, we fired the thrusters to begin backing away from the surface. we were still moving forward at 4 centimeters per second. So it took 3 more seconds for the thrusters to remove our velocity. So we reached 0 velocity 9 seconds after contact. Our best estimate is that we penetrated 48.8 centimeters. And it wasn't until 16.6 seconds after contact that we actually rose back above where the original contact surface was. This is the view from the nav cam. So this is off to the side. You can get a sense, you can see the TAG-SAM shadow coming in here. And so you can also just get a broader field of view and a sense of how the asteroid surface responded to the tag event. Boom. Lots of material was mobilized. Initially, a very large particle size distribution. And then as we got deeper, the particle size seems to decrease dramatically. And as we start to back away, you can see the shadow of the TAG-SAM now on a very disturbed, moving asteroid surface. It starts to look quite sandy. And I was like, the beach was there the whole time. It was just buried underneath the subsurface. Not even that deep, just centimeters down, we got to a much, much finer grained area. And now I want to draw your attention to what's happening in the upper right. There's some really cool stuff. So this is the undisturbed asteroid surface you can see coming into the field of view here. You can see some of these larger rocks are moving, like this one that my cursor's on is a flaky particle that's tumbling. And then I'm going to draw your attention to a particle that's going to show up right here in the upper part of the image, right there. It crashes into that boulder and shatters. So we have a really nice natural collision experiment going on here as well. So the TAG-SAM contacted the bottom of this image, and then up here, this is dug out by, I think, by the thruster plume. This is where one of the thrusters was hitting the asteroid surface. And so you kind of get this wall of material that's pushed between 2 gas plumes, and in fact, 5 gas plumes, because there was 4 thrusters that hit the surface. So 2 days later, on October 22nd, we put the TAG-SAM in front of the SAMCAM, and we saw what I thought were these frightening images, because we could see that what was supposed to be a check valve, a flap that keeps the sample secure, was wedged open with some really large rocks, and particles were escaping out of the TAG-SAM. I could see in this field of view alone, just by measuring all of the particles, which are very flaky, in morphology, we had about 10 grams of visible sample just right here. So I looked at our spacecraft lead engineer, Sandy Friend at Lockheed Martin, and I was like, how fast can we stow? Because we're bleeding, and we want to stop the bleeding as fast as we can. We did a quick assessment of all of those images. That was just a few of the images from the characterization campaign, and convinced ourselves that we had a lot of material still in the TAG-SAM head. First of all, it's totally dark and opaque inside there. When we looked at it when it was empty, we could see inside there. So just to block the screen, we estimated it would take about 57 grams. So right there, we're very close to our requirement. We can see 5 large particles holding that flap open. We estimate those have a mass of 28 grams. And where they are wedged open and we can see inside the collection volume, we can see a lot of material in there. We estimate that's about 312 grams, filling about 17% of the observable volume. So direct imaging suggested at least 400 grams of material was in the TAG-SAM head. We were confident we were well above our requirement, and we went ahead and made the decision to stow. So I think I said all of this here, so let's just get right to it. After that, we decided TAG-SAM was good to get into the sample return capsule. We put TAG-SAM in. Notice that some particles escape even through that final click in. We pulled on it to make sure it was safely secured in the capture ring. And then we separated the tube and we removed the bolt holding the head to the arm, closed up the sample return capsule, and we said goodnight to TAG-SAM. We'll see you in September of 2023. So with that, thank you for your attention, and I'd be happy to take some questions.
Thank you so much, Dr. Loretta. We've had many questions coming in, and so we've picked a few here for you. I think we've got time for maybe some 3 questions that we can squeeze in there. So the first one comes from Suba Commander, who asks, if you had no engineering constraints, what asteroid or body is the most interesting for you to explore besides Bennu, of course, and why?
Wow, no engineering constraints. It's almost impossible for me to wrap my mind around that. I would want to go to all of them, right? Or at least go to representative of each type of asteroid, right? Because I mentioned it, I didn't go into it, but I said on one of the slides, Bennu is a B type. We have a whole asteroid alphabet that, there's S types and there's X types and there's C types and there's M types. So I'd want to see what all of those look like. What are they all made out of? And ultimately get samples of all of those into our laboratory. So we really have the geological diversity of the asteroid belt available for study. So if I'm not limited, I want them all.
Don't we all? I guess so. Our second question is from Siddharth Krishnamurthy, who asks, how confident are you that the crater material is native Bennu material and not adulterated or stolen, from the lack of a better word, by whatever body that impacted Bennu?
That's a great question. The craters, the small craters, definitely look very different than the average surface. They're much redder in our color imaging, and they're generally of where the fine grained material is occurring. The good news is we see that we can see a sequence of changes in the color and spectral properties of the craters as they appear to degrade. So the really fresh craters appear very red in our false color imaging. And Nightingale is like a classic example. It looks really red compared to the average surface. And I think you could tell from the data I showed, it looks like a very fresh crater. And then as the craters degrade and they appear to get weathered and older, they get progressively bluer until ultimately they start to look like the background. So we think we're seeing a phenomenon we call space weathering, and that the craters are sampling the subsurface. And we see from the TAG event that as you go deeper in, the grain size decreases substantially. There's a lot of fine grain material just underneath the surface. And so I think as it gets exposed to the space environment, the minerals are altered. We're probably taking those phyllosilicates and we're making like iron oxides and metallic iron and maybe iron sulfides. And that's driving you to the bluer spectra that we see that dominate the surface. And I think that magnetite, that iron oxide mineral especially, could be contributing to that bluing.
Wonderful, thank you. So our last question is from Doug Isbell, who asks, could you please elaborate a little bit more on the landing sequence that's for the sample return? Are we using a parachute? And is it going to be a ground impact landing at the Utah Testing and Training UTTR? I'm not quite sure what the last R is.
Yeah, our sample return capsule is based heavily on the same design that was used for the Stardust NASA mission, which returned comet dust from the coma of Comet Wilt 2. And so if you're familiar with that mission, it has the nice heat shield, which drops most of the kinetic energy. When we're coming in at 12.4 kilometers per second, like 28,000 miles per hour when we hit the top of the atmosphere. And the heat shield will heat up and absorb most of that energy and slow the capsule down. Once we reach a free fall velocity, we'll deploy 2 parachutes. There's a drogue chute and then a main parachute. And we should come down for a relatively soft landing in the Utah desert in 2023.
Awesome. Well, thank you so much, Professor Dante Lauretta, and to all of you for joining. That officially concludes this webinar. Please take the time to fill out a survey when you leave our lecture. This is our last webinar of 2020, so we hope to see you at our next webinar, the Ultraviolet Spotlight on Exoplanets, on January 25th, 2021. Thank you all and good night.